Good afternoon. What is the last thing that we did last time? I remember that we talked about subspaces and affine subspaces, and I think affine subspaces was the last thing that we talked about, right? Okay, let's begin discussing how to find extreme points and their algebraic counterparts, basic solutions and basic feasible solutions. Actually, basic feasible solutions are the counterpart of extreme points. So let me just take a polyhedral set. So extreme points of polyhedral sets. That's what we want to discuss today. Let's take a polyhedral set. So let P be a non-empty polyhedral set in n-dimensional space defined by the intersection of finitely many half spaces and hyperplanes. So let's assume we have AIX less than or equal to BI for I in, say, index set I sub 1. And then we have AIX greater than or equal to BI for I in another index set I sub 2. And then finally AIX equals BI for I in, say, I sub 3. I1, I2, I3 are pairwise disjoint. They are mutually disjoint. And their union just gives you a set, say, I, which consists of all constraint indices. Okay, some of them could be empty. There's no problem with that. But we assume at least one of these sets is non-empty. Okay? Okay. Let me give you one additional definition here. Let X bar be a point in Rn. We say a constraint I is active at point X bar if that particular constraint holds as an equality at X bar. Okay? So, for any such point, let's define J of X bar to be the set of active, the set of indices of active constraints. Some people refer to active constraints as binding constraints, which is fine, so we may use that term as well. I don't know if there's any other term anyway, binding or active. Since we always require a solution to satisfy the third set of constraints, the equalities, we always assume that J of X bar includes the set I sub 3 as in it. Okay? So this set always includes I3, indices in I3, by definition, okay? By convention. So actually, maybe we should say let X bar be a point in Rn that satisfies number 3, where these are numbered 1, 2, and 3. Let's just put it that way so we are agreeable with the convention we have in mind. Okay? Now, it turns out that when you look at polyhedral sets, and if you're interested in looking for an extreme point, well, we are interested in finding extreme points of polyhedral sets for one reason. Because a linear programming problem, whenever it has a feasible solution, it will have at least one extreme point solution, provided that the system is in standard form. For non-standard forms, sometimes the existence of feasible solution need not really imply the existence of an extreme point, which may be problematic. That's why we work generally with standard form problems. But more importantly, whenever there's a finite optimum solution, whenever there's an optimum solution, it turns out that at least one extreme point of the feasible set qualifies as an optimum solution. Okay? So you want to be able to have a way of identifying extreme point solutions. We have a definition for extreme points. It's the kind of point which cannot be expressed as a strict convex combination of two distinct points of the convex set of interest. However, that is not really operational. You know, it's a definition by negation. But here we'll start talking about how to find them. The general idea is this. If you have a point x bar of the polyhedral, well, not necessarily of the polyhedral set, but a point x bar which satisfies all of the equalities. And if you look at the active set of constraints here, which surely includes I3, but may also include some of the other sets, I1 and I2, as long as a constraint satisfies those inequalities as actual equalities. Okay? When you look at these collection of constraints, the active ones, if you look at the normals of these constraints, the AIs, if you put them in a set, then you have finitely many, which is the same in number as there are elements in J of x bar. If this set contains n linearly independent AI in it, then the intersection of these equalities corresponding to the active ones will normally give you an unique solution, and that unique solution will be your extreme point solution. That's the general idea. So as long as you know the point under consideration, as long as you know which x bar you're looking at, then you can surely compute your active set relative to that point, and then see if you have n linearly independent AIs in that set. But sometimes it may so happen that you don't have a point under consideration. So you might want to try, in that case, the intersection of n linearly independent constraints picked from the union of these three sets. But the n linearly independent AIs you're looking for should always include the set I3, okay, as a subset. So plus other ones, that completes to n. Now, when you solve n linearly independent, well, actually, when you pick some n constraints and assume that they're active, two things could happen. First of all, those that you pick may or may not be linearly independent. If they are not linearly independent, if they are linearly dependent, you've got n of them, then two possibilities arise. Either there's no solution, the equations are inconsistent, or you've got multiple solutions. Okay? Either way, you don't have an extreme point because you don't have a unique solution. You want a unique solution. So the linear dependent case with n constraints and active constraints, candidate ones, will not work if they are not linearly independent. If they are linearly independent, then normally you get your unique solution for those. Now that unique solution may or may not satisfy the remaining constraints, the ones that are not binding or the ones that are not active. Okay? If the solution satisfies the ones that are not active at that point, then you have a basic solution, or in that case you don't have an extreme point actually. If the solution does satisfy all of the remaining ones, the ones that are not active, then you have an extreme point. Now this discussion I hope you will remember, because that basically wraps up the main ideas. So let's go through some of the details here. Okay, so let me begin with a theorem. Did we have a theorem 1 before? Yes. Well, actually, before theorem 1, I had another auxiliary theorem, which I did not number. Nevertheless, this is going to be your theorem number 2. So let P be a non-empty polyhedral set or polyhedron in Rn, and let x bar be a point of the polyhedral set. So we assume x bar is actually in the set. The following parts are equivalent. A, there are n linearly independent constraints. Linearly independent constraints means their normals are linearly independent. There are n linearly independent constraints in the active set. Okay? And constraints are linearly independent by definition if their normals are linearly independent. Okay? That's how we define constraints being linearly independent. Part B. The span of the normals of the active constraints gives you the n-dimensional space. And part C, the system AIX equals BI for I in the active set has a unique solution. In which case, of course, since x bar is already a solution to this system, that unique solution has to be x bar. Okay? Okay. Now, first of all, the equivalence between these statements mean that they are if and only type statements. So A holds if and only if B holds, if and only if C holds. Okay? That's the kind of thing we want to prove. So to be able to prove that they're all equivalent, you need to prove sufficient number of relationships, which implies that anything here, any of A, B, C, implies any of the other ones. Okay? You have to prove a sufficient number of them. What am I going to do? Let's see. I want to go ahead and prove A implies B. And then I want to prove that B implies, let's call this one number 1. And then I want to also prove that B implies A. Emre, why don't we open a window? I think people seem to be sort of getting heavy a little bit. It's the afternoon. Maybe, you know, a heavy dose of lunch may help with a little bit lethargy. Okay. I had a heavy lunch myself. And believe me, it takes the blood away from your brain. And I hope, you know, we won't make a mistake for that reason. All right, so A implies B, B implies A. And then I'm going to also prove, let's see, not B, the negation of B implies not C, and vice versa. Okay, so let me call this number 3. Let's call this number 4. So you need to prove 4 parts. Now, not B implying not C and not C implying not B means B if and only if B holds, if and only if C holds. Okay, so since B is also included here, of course, everything will be okay as far as proof construction. Okay, so let's begin with number 1. A implies B. What do we have in A? There are n linearly independent constraints in Jx. So let, by assumption that A holds, there's a subset, say J star of J of X bar consisting of some M, some N linearly independent constraints. Of course, these are active constraints. We picked them from J of X bar. Okay? So, by assumption, there is a J star whose cardinality is N, and these N constraints are linearly independent. So, if you look at the span of the vectors AI, I belonging to this set J star, since J star contains n linearly independent such indices, of course, their span is Rn. Okay? N linearly independent AI will generate every possible point in Rn. Now, you can also see that span of AI, I in J star, is a subset of the span of AI, I in J of X bar. Why? Because J star is a subset of J of X bar. That's why. So the span is a subset. When I say subset, of course, I don't mean not equal. I don't mean proper subset. Subsets are subsets. Could be equal. Okay? All right. We just proved that this part is already Rn, and this part cannot be any more than Rn because all vectors are vectors in Rn. So obviously, you've got equality here, so all these relationships hold as equalities because you've got Rn here, Rn here. Okay? So Rn, so you've got equality, and that proves B. Now the second proof. In the second one, we assume span of AI I in JX is equal to Rn. And we need to show that there are n linearly independent AI in this set. That's obvious. From where? If you look back to your theorem 1, part A actually says that. Do you remember that? So, since well, by the way, there's a word missing here. You should write span here. Okay? Obviously, without that, you don't have equality. The span of these things are n. So, the dimension of this set, let me give a name to this. Let's just call this set S. I don't want to keep writing it all the time. So the dimension of the span is equal to the dimension of Rn, which is obviously n. And theorem 1, part A, implies what I just told you. Implies that there's a basis consisting of, there's a basis of S consisting of some n linearly independent AI chosen from here. So basis always has linearly independent vectors, so this part is also proved. Part 3, not B implies not C. What is not B? So let's assume span of AI I in JX bar is a proper subset of Rn. It's not equal to Rn. It cannot be a superset of Rn, so it has to be a proper subset of Rn. Okay? What do we want to show? Part C. The system, well, actually, we want to show not C, which means we want to show that the system AIX equals BI for I in JX has not or does not have a unique solution, which means either it has no solution or it has multiple solutions. First of all, if this is a proper subset of Rn, it is possible that this span is empty, or is it possible? It is possible. If I3 is an empty set, then you picked an arbitrary point x bar in Rn, in which case, of course, none of the constraints may hold as equality at that point. So it is possible that this is an empty set. So in that case, am I done or not, if that is the case? If this span is empty, again, by definition, let's just call it S. Okay? If S is empty, what is the conclusion? Does not C hold? Obviously holds. There's nothing to solve for in that case, okay? Because if there's no vector here, if there's a single vector here, even if there's only one vector, you have a non-empty span. So the only way you can have empty is by having nothing in Jx bar. So then Jx bar is surely null. And so in part C, there's nothing to solve for, which means there's no unique solution, okay? It's just a play with words. When something, does not apply, it holds, okay? So, in the remaining case, S is non-empty. And because it's a proper subset of Rn with S removed, this set is also non-empty. There's something in it, okay? In this case, then there is a non-zero vector D in this set, Rn minus S, which is orthogonal to every vector in S, or which is orthogonal to S. Okay, the span. S is a subspace. So if it's a proper if it's a subspace with dimension less than with dimension less than n, then you've got this situation. Okay. Consider a solution y to ai x equals bi with I in Jx bar. Is there a solution for sure? X bar is a solution to this. So a solution obviously exists. And so I'm just giving if there are multiple solutions, I'm just considering a possible solution here, okay, which may or may not be your X bar, okay? Then, if you add the non-zero vector D to this solution, this is also a solution to this system. Because AI times y plus d gives you AI y plus AI d for I belonging to the active set. Well, what do you know about AI d? D is perpendicular to each one of them, so it's 0. So you've got AI y, but how much is AI y? It's bi, because y is a solution. So this holds true for each I in the active set. So what did we just show? If there's a solution, well, if y is a solution, then y plus a non-zero vector d is another solution. So you've got multiple solutions, which means not C, okay? So whenever not B holds, not C also holds. Okay? What are we left with? Number 4. So we're going to assume not C and we'll prove not B. What is the case for not C? Assume not C holds, or the negation of C holds. then either there is no solution to that system or there are multiple solutions. The possibility of no solution is ruled out. Why? Because somebody tell me. Because X bar is already a solution. Okay? Because at X bar, all these constraints are active, so X bar satisfies them. Okay? AI X bar equals BI for all such constraints. Okay? In the remaining case, you've got multiple solutions. So let's pick two of them. Let x1 and x2 be two distinct solutions to this system. Distinct means they are not exactly the same. They are different in at least one component. Okay? So let's define D to be the difference of x1 and x2. Since x1 and x2 are different, D is non-zero. It cannot be equal to 0. And what else? And AI times D is equal to AI times x1 minus x2, which gives you AI x1 minus AI x2, but how much is AI x1? BI. AI x2 is also BI because x1, x2 are solutions, so this gives you 0. Thus, D is non-zero and D is orthogonal to AI for each I in the active set. So what's the conclusion here? So you just generated a vector which is orthogonal to each one of them, and it's non-zero. So obviously the span of these vectors cannot express D as a linear combination. Okay, you cannot express D as a linear combination of these vectors. Hence, D cannot be expressed as a linear combination of the vectors AI, I in Jx. So D is not in the span of these vectors. Which means not B holds. You don't have equality here. okay? Because D is not generatable. Questions? All right, so anyway, let me illustrate a few things about these. Suppose I've got, say, 5 half spaces. And your feasible set is this region here, the set of solutions. And suppose the point x bar under consideration is this one. Let me just number the constraints, the inequalities, where this one is number 1, number 2, which one is number 3? Number 3 is this outside one, number 4, and number 5. Now, in this case, I've got I2, the greater than or equal to type constraints, consisting of the constraint indices 1, 2, 3, 4, 5. So all of the constraints belong to I2 in this case, okay? The greater than or equal. Was it the way I gave you? Greater than or equal was the I2 set, or was it the I1 set? Which one? I2, okay. All right, so this is I2. There is no less than or equal to constraint here, and there is no equality constraint here, so they are empty. Okay? Now, if you plot the AIs for this system, well, I'm going to actually erase these lines because they may confuse you. Let's just pick the origin, which is this point actually. This is the origin. At the origin, A1, which is the normal for this number 1 constraint, it points this way. So that when you move alongside that A1, you are increasing yourself, since the constraint is of the form A1x greater than or equal B1. Well, 0 actually. B1 is 0 for constraint number 1. And A1 is the unit vector 1, 0 if you take it in 2 dimensions, or it's the first unit vector in higher dimension. Okay? All right, so when you move in the direction of A1, you're increasing this value on the left side, so you continue to be greater than or equal B1, okay? Because at the point you are greater than or equal. All right, for this reason, A1 points this way. A2 points downwards into the shaded region and perpendicular to the defining hyperplane, so it looks something like this. Okay. A3, associated with this redundant constraint, points something like this. A4 points this way. These should be orthogonal to the defining hyperplanes. And A5 points which way? Up, right? That's your A5. All right. What are the active constraints at point X bar? You've got 1, 2, 3, and 4. These are the active constraints at that point. So, in this example, n is equal to 2. We're in two-dimensional space. Okay? And since n is equal to 2, the theorem says look for 2 of these active constraints and see if they are independent, or actually they should be independent if that's an extreme point. And it looks like an extreme point, right? So you can pick any 2 of them. So if you pick 2 and 3, for example, that means you're picking number 2, which is this guy, and 3 is that guy. So are these linearly independent? For sure. One is not a multiple of the other one. Do they generate the entire two-dimensional space? For sure. When you take linear combinations of these, you can generate any point. So part A, part B equivalence is verified. What was part C? Is there a unique solution to these? Well, if you take number 2 and number 3 as equalities, they intersect at that particular point, so there's a unique solution. And so part C also holds. Okay? So also you could have worked with 2 and 4, which again proves that, or it will work for all parts of the theorem. Also 3 and 4 will work. Okay? So in this case, any 2 will do the job actually. All work. All pairs. Well, all of these possibilities work. Okay? Let me pick. Well, by the way, the unique solution in part C is necessarily x bar. There's no other solution. Okay? They intersect at that point. Now let's talk about the algebraic counterpart for extreme points. Basic feasible solutions are the corresponding algebraic object for extreme points. Basic solutions, they don't correspond to extreme points unless they are also feasible. Okay? So basic solutions could be points outside of the feasible region from time to time. But first, let's see how we define these things. Let me just give some pointers here. Theorem number 2 suggests to look for n linearly independent active constraints. Active constraints, not constants, but constraints. Once I write constraints like that, and somebody interpreted that later as constants. No, they are not constants. All right. Because part A of the theorem says you are looking for n linearly independent constraints. And you know that their solution is unique. So you want to fetch some n active constraints. If they are linearly independent, they will have a unique solution. Such solutions are called basic. I'll give you a more formal definition, but that's what they are essentially. And given algebraic characterization of extreme points. Which are geometric objects. Okay? If such a solution resulting from solving the n linearly independent equations. If such a solution also satisfies the inactive constraints, as well, then it is called a basic feasible solution. So, you picked n linearly independent constraints. You assumed they are active. You set up your equations, n equations in n unknowns. You get a unique solution. The solution either satisfies the constraints that are ignored, the ones that are not active, or the solution violates at least one of them. Okay? If the solution on hand satisfies all of the remaining constraints, yes, you have a basic feasible solution. If not, you have only a basic solution, which is not feasible. Okay? That's the basic idea. So let me give you the formal definition, and then we quit. Here's the formal definition. Let P be the polyhedron in Rn defined by the system AIX less than or equal to BI. This is the same system we're talking about. I1 AIX greater than or equal to BI for I in I2, and AIX equals BI for I in I3. Let X bar be a point in Rn which satisfies three if I3 is not empty. Okay? And let J of X bar be the index set for active constraints. So, the definition of a basic solution: the point X bar is a basic solution if 1 J of X bar includes all indices in I3. So that's a necessity, that's always assumed. Part B, there are n linearly independent constraints in Jx bar. Part B, X bar is a basic feasible solution if it additionally satisfies all the remaining constraints. This definition is quite different from what you might have seen in undergraduate or perhaps elsewhere. Because in undergraduate education, we typically define basic solutions relative to standard form constraints. Okay, AX equals B with non-negative variables, x greater than or equal to 0. In that case, the basic solutions could be defined in more easily than here. But this is the general definition. It applies to any polyhedral set. Okay, and we'll see some ramifications of that in the next lecture on Monday. See you on Monday then. Okay.